There we go. So when we look at, when we look at these 4 steps here that a processor flows on, in terms of fetching an instruction from memory, decoding it, executing the command with some sort of logical mathematical operation, storing the result somewhere in the memory, each of these steps happens at a fixed rate. And that rate is the clock for the processor. So when you talk about a 3.2 gigahertz clock or processor, you're talking about the clock rate of that processor. So 3 gigahertz means that roughly 3 billion times every second, one of those operations occurs, which is like a ridiculous number of operations, right? That's why we can do so much with our computers these days, as opposed to, 20, 30 years ago. So the clock speed is determined by that number that we see when we're shopping for like different processors. The CPU has a higher clock rate than everything else in the computer. So nothing else occurs at that same clock rate, but the CPU's clock drives everything else. So even if the speed at which we communicate over the PCI bus to our graphics card or to the network card, yes, it's going to be at a lower rate, but it's still based on the CPU clock. So, in general, the higher the clock speed of the CPU, the more stuff you can do every second, the higher performance your processor is going to be, right? Which also means the more expensive it's going to be. Right? It's not the only factor, but it's certainly a factor. Here's the other really cool thing. This has been an innovation in the last several years. Originally, a processor had one core, meaning these different like arithmetic units and the control part. It just had one of each of those. And if you wanted to do more processing, you would actually install multiple processors. So there's actually motherboards, and we'll see some examples of these, where you can have like 2 processors or 4 processors. That's not quite as useful as it was 20 years ago, because now all of our processors practically have multiple cores, meaning in one physical processor, there's basically multiple logical units of ALUs and control systems and all of this. So processors today certainly have 2 cores, maybe 4 cores, maybe 8 cores. And so that's another thing to consider. And this is where we start to learn what makes it tricky to design high-performing CPUs or budget-friendly, high-performing computers or budget-friendly computers, is the higher the clock speed, the more instructions that can be executed at a time. That's going to help. But if you have a bunch of cores, that means the processor can be doing multiple different things at the same time. Which one is more important? Like so many things in computers, the answer is it depends, right? If you're using your computer primarily for a single task, and that task has to happen sequentially, multiple cores isn't going to really matter, right? If you're using your computer to do video processing, which is inherently can be parallelized, meaning you can like apply those algorithms all at the same time, multiple cores is going to make a huge difference, right? So it really depends on how you're using the computer. But in general, a multi-core CPU is going to be higher performing than a single-core CPU. So another way that we gain performance. Oh, and I guess one more thing too. Another advantage of the multi-core thing is these multiple cores are on the same piece of silicon, the same physical chip, which means when cores communicate to each other, it's extremely fast because it's using the silicon itself and those very high-performance neural pathways to send that data. When you have multiple physical chips, you have to use the bus on the motherboard that we talked about like a week ago to communicate that data, and that is inherently less fast. So another advantage of the multi-core stuff. All right. This section here that we're about to talk about is actually up here on the motherboard thing I know I think I mentioned this like a week or so ago, but I wanted to revisit this idea of control bus, address bus, and data bus. And so here are like better definitions of these. But basically, like I said, the CPU is the brains, it's like Grand Central Station, right? So it is the brains of the motherboard. It needs to communicate with everything else on the motherboard, and it does that with the buses that we've been studying, and we can roughly categorize them into 3 different bits. Some of the data we send are addresses. Where in the computer's memory do we want to read data or write data? Where on the graphics card do we want to update the image? That's what we use the address bus for. The data bus is like, here is the data we want to store on the hard drive. Here is the data we want to store in the RAM. Here is the data related to the image we want displayed on our monitor. Okay. And then the control bus is more focused on changing the state of those components, like telling the RAM, hey, I'm about to read from you, or hey, I'm about to write from you, or hey, hey, graphics card, can you confirm that you've received this data? Is it okay for me to do the next thing? Or, hey, network device, oh, you just told me we got a new packet. I better go read the new packet because it's time to update the web page, right? So that's more of control bus stuff. These 3 things together, we can think of as the system bus. Yeah, so these are like the 3 subcategories. This is, I think, a good way to think about it. So, excellent question. Oh, sorry, I should have repeated the question. So the question was, what about the system bus? And the system bus, think of the system bus as a combination of the control bus, the address bus, and the data bus. So, yeah. All right, here's another way that we make our computers even faster still. RAM, DIMMs, are certainly pretty fast these days. Certainly faster than hard drives and even SSDs. However, by putting memory right on the processor, that can be accessed even faster. Again, because it's physically co-located on the silicon, we don't have to go across the motherboard to get some data. So the most frequently used data, the processor will actually store in what's called the CPU cache. And then only when it's not needed there anymore is it going to get written to the RAM. And this can make a big performance. So you might hear about this referred to as like level 2 cache, level 1 cache. Basically, how close is it to the processor where we can store this data? Yeah, the most frequently used stuff, right? So like if we're performing a mathematical operation, we're going to store that in the cache because we're probably going to use that answer in a moment to do something else. So that's another thing to look at when we're trying to decide what processor to buy. Not only what is its clock speed, not only how many cores does it have, but how much cache does it have. The more cache it has, the faster it's going to be. But this memory, this type of memory on the processor is like really expensive. That's why we still need 16 gigs of RAM in the computer, and we're not going to have 16 gigs on the processor. Like prohibitively expensive. So, but another way we make our computers fast. Okay, so I got a bit ahead of myself. So we can have different levels of cache. This is all focused on how close is it to the processor, meaning how fast can it be accessed. I'll be honest, you should be aware of there are different levels. Do I want you to memorize that the level 2 cache is approximately 10 clock cycles? No. What I want you to take away from this is that level 1 is really close to the processor. It can be accessed really fast. It's small and it's expensive, which is why it's expensive, which is why it's small, and it's fast. Level 2, not quite as close to the processor, takes a little bit longer to access, but we can have more of it. Level 3, farther away from the processor, shared by all the cores in the processor. They're all going to share that level 3 cache. But again, it takes like 10 times as long to access level 3 as it does level 1. But all of this is faster than going to the RAM in the computer, and all of this is way faster than going to your drive. So keep everything in perspective. So those are our cache levels. Let's see. So here's a graphic, I guess, showing a couple. This is kind of a block diagram of some AMD and Intel processors. So just to show you, like level 1 and level 2, each core gets their own level 1 and level 2. Level 3 shared by all the cores. So. All right. Cool. Just want to see where we're at. CPU registers. So inside of the processor itself, when it does those fundamental calculations, like the addition, the subtraction, the condition stuff, in order to do each operation, it doesn't read that data has to be stored somewhere to do the addition. I need the value of X and Y before I can add them together. Inside the processor, there's another storage called registers, and that's where we store the immediate values that we're about to add together or subtract or do some other operation with. Each processor architecture has a certain set of registers. These are accessed faster than anything. Think of them as like part of the arithmetic unit or control unit. It's not like a cache thing. These are super fast, single clock cycle, we're going to do the operation. And different processor architectures have different numbers of registers. So, one thing that we also store in the register is what's called the program counter. So when you're running, when your operating system is running and you're in your Google Doc typing your notes, the processor needs to keep track of, here's the instruction in the Google Doc software I'm currently running, and here's the next one I'm about to run. And that's stored in the registers as well. So we keep track of where we are, and we keep track of what's the address of where we're going next. So. Being aware of registers is useful, not super relevant to what we're going to be doing. All the processors have them. This isn't like a criteria we're going to look at when we try to decide which one is a good fit for our systems. All right, here's something else that you may have heard of. It's worth commenting on. So let's look at like Intel. When Intel is manufacturing processors, the way they do that is they make their processor, and then they make a whole bunch of them, and then they test them, and they test them and see where they no longer work correctly. And let's say they work fine at 3 gigahertz and they don't work at 3.2 gigahertz. They're sold as 3 gigahertz processors. But the ones that work at 3.2, they're sold at 3.2, right? They don't like specially make them, they just do it through testing. What that means is often, even if your processor is a 3 gigahertz processor, you could run it faster, and it might be okay. And so this is what overclocking is about. This is the idea of running your processor with a higher clock speed than what it's supposed to be run at. And sometimes this works out great, and sometimes not so great. But that's something that a lot of people do with their own custom-built PCs to get every extra ounce of performance. As it mentions here, sometimes you have to increase the voltage to keep it running well. Sometimes you have to increase the cooling so that the higher the clock rate, the faster the processor runs, the more heat it generates, the more important it is to get that heat out of your computer. But there's a lot of resources online if you're into overclocking your computer. Please don't overclock your computer from the school, though. Leave it be. So. All right. Yeah. So here's why would you not want to overclock? You could damage your processor or motherboard. Like, it's possible. You could overheat something, which would cause damage, and that's a problem. you probably violate your warranty once you do it. And then, like, AMD is not going to take their processor back from you. So, beware. All right, last thing I wanted to touch on today is how do we, so processors generate a lot of heat. One of the most thermally significant parts within the computer. And so the question is, how do we get that heat out of the processor so that it doesn't overheat and damage itself? We saw some of this previously. We saw that we have on our processors, we have the heat sink. That's that metal piece bolted to our processor. It's got thermal paste, and I'll demonstrate this later, but it's got a nice thermally conductive layer between the top of the processor and that big piece of metal. It has all those little fins in it because that gives you lots of surface area for heat to be transferred away from the processor. And then on top of that, we bolt a fan to draw cool air around all those fins and blast the hot air away. We also have a second fan in our case to pull the hot air out of our case and replace it with cool air as well. So in terms of cooling methods, passive cooling means we just rely upon thermodynamics, good old-fashioned conduction and convection to transfer that heat, to do the heat transfer away. Heat sink, super easy. Our desktops have the heat sink and the CPU fan. The thermal compound is between the processor and the heat sink. Then there's more advanced stuff. You can have heat pipes, and you can see that in this picture here. These are like, copper is very conductive. These are copper pipes that literally draw heat in this laptop away from the hot spot and to the edges where the fans are. So that's some way of doing it. You can also do liquid cooling. I thought I put a picture of that in here. Oh, maybe I didn't. I'm sorry. You can actually have like a water-cooled desktop computer where you actually circulate a liquid because liquids are fantastic thermal conductors to transfer the heat from your processor out. Just to be super clear, like the liquid is inside of like these little pipes. We don't want liquid inside of our desktop and on our motherboard. But we can run it through the pipes. We can cool our processors. And there's some really cool pictures of like liquid-cooled processors and computers out there. I'll add one to the slides. I thought I did that, but apparently I didn't. So, what questions do you all have about the CPU overview stuff before we jump into other things? I did have a picture. It's just hidden. Here, I'll put this back up on the screen. So here's a picture of liquid cooling. And so you can see that they actually have like a reservoir of the liquid. They have these tubes. They have these tubes here carrying the liquid through and a pump to circulate it. So kind of cool. And they make it like fluorescent, of course, so it looks awesome. But anyway. Any questions I can answer at this point about our introduction to CPU stuff?
Real quick.
Oh, hold on. Riley's asking one question here. Let me answer his, and then yes, absolutely, you can jump in.
I would say it's probably is it like harder to like take the disassemble and apart, like with the liquid cooling?
Oh yeah, like for sure. Personally, I'd be afraid I wouldn't like have something sealed right, and I'd end up with like destroying my whole computer. Yeah. So, but there are tons of people who do it, and it works great, and it looks amazing. Just not on my personal list. So Riley's question was like, if you have liquid cooling, does it make it harder to like service your computer, take it apart? Absolutely. All right, other question. Umar, was that you?
Yeah, I got kicked out of the class for like 20 minutes. So is this slide presentation available on like daily agenda or something?
It is. So two things that will help. It's linked right here. are the slides, and I've recorded this as well, which I should probably stop doing because we're done. And so it'll be up on YouTube later today as well.
All right. Thank you.